Cook. We're all from the Bachelor of Creative Technologies program here at AUT, and we've prepared a little standalone application for you to watch. And all our work we did this weekend from scratch.
Captain Cook is a deployable greenhouse designed for use on Mars. The name Captain Cook derives from a famous Kiwi historical figure and also involves an aspect of luxury which we are aiming for in our design. In addition to this, it has a slightly funny and quirky element which inspired our design process. The project was developed in response to the Deployable Greenhouse Challenge as part of the International Space Apps Challenges. The idea of this challenge is to create a conceptual design for a deployable greenhouse for use on Mars or the Moon. The greenhouse is to provide supplemental food for astronauts, as well as providing additional support for their life support system. We approached this challenge with a design ethos. We were interested in the human aspect of the experience, how astronauts would use the space and would use the greenhouse specifically. We were interested in using disruptive thinking to approach it from a position of ignorance initially, where we could come up with counterintuitive ideas and revolutionary thinking. We viewed technical design as an iteration of an overall design process, as opposed to a final and resolved technological advancement. Captain Cook was designed with 6 configs in mind: a flight config for when the module was deployed on the planet, a deployment process for when the module unfolds, a day config for during the day, a night config for during the night, an event config for during dust storms or other events, and a service config for when astronauts are tending to the plants. The overall intent of our design was to enable a space which could be used not simply as a place of caring for plants, but also a place which could be used for relaxation, recreation, as well as a kitchen area for preparing meals. Our overall design is a cylindrical shape with a roof that is able to be raised and lowered. Connecting the roof to the bottom part is a clear membrane which ensures pressurization is maintained. The walls have rails attached to them, and these rails have mounting points for plates which can carry seating trays. During the flight config, these seating trays are attached to the top of the rails, which are lowered. By being attached to the top of the rails, there is a space below which enables room for storage of seating water, seating material, and machinery and computational equipment. The deployment process involves raising the roof, raising the plates, opening the external hatches, which allows the transfer of water and seating material from the inside to the outside, as well as connecting the access hatchway to a pressurized corridor. Once this is done, it is essentially within its daytime config, with plant trays raised in the sunlit area and space within the capsule for astronauts to move around. For tending to plants, astronauts are able to lower a single column of plant trays. This allows them to have ample room within the capsule while tending to plants, as well as to sit down and enjoy the view. In the night and event config, the rails lower, lowering the plates with them, and the roof is lowered as well. While this protects the interior from excess radiation, captures heat, and provides protection from elements such as dust, the space taken up by the plates means that astronauts are not able to gain entry into the module. Our design process began with a brainstorming session where we came up with ideas, words, and concepts around deployable greenhouses. Due to the diverse nature of our team, this resulted in a vast amount of content that we were then able to condense down into a few solid ideas, thanks to collaboration with lecturers, as well as watching some online feeds from NASA. The online feeds from NASA in particular helped to give us significant direction in our project. It was evident from our brainstorming session that we were interested in luxury over functionality. We wanted to design an experience for the astronauts, rather than simply create something that produced the largest amount of edible biomass. Our solution centered around this idea of gardening in space. We wanted to enable the astronauts to be able to do some gardening as well as providing them with an opportunity to grow a diverse range of foods for their personal tastes. We believe that our project can have a great impact both for astronauts and for people on Earth. For astronauts, this impact centers around a connection with home. While technology can provide communication, it can also be very disconnecting for astronauts due to the sterile environment. Instead, we want to provide a space that allows astronauts to connect with Earth life through a natural environment, as well as providing food sources which will allow the astronauts to experience some of Earth culture. For those back home, we intend to rebrand space. Rather than seeing space as this distant place which is isolated, we want people to be able to see space as just another place. We want to see humanity spreading into the stars, and those who are in space to be considered as part of the human community, rather than distant and disconnected. This project has a number of logistical considerations. From a technical perspective, we are assuming that there would be an ample power supply for any human colony landing. Thus, our module is not completely self-sustaining, but rather would rely on external power being supplied. In addition, we see a great benefit in enabling the module to be connected directly to the habitation modules, which would mean that there would not be a necessity for an airlock and would allow oxygen to be transferred through ventilation systems directly. Location on Mars is another consideration. Depending on the location, there could be very different environmental factors, and this could influence the design and materials used in the module. There are also ethical considerations when living on Mars. Sustainability is key. Colonization raises many ethical questions, such as ownership and entitlement. Our future scope with this project involves many areas. We foresee crowdsourcing becoming a major influence in developing technologies, including this one. Specific to our project is the relevance of 3D printing. 3D printed parts could be very useful, as it could enable replacement parts to be printed on Mars rather than carrying a number of spare parts. You could even investigate 3D printed structures. While not feasible currently, this technology is rapidly developing. Finally, we see further developments in our module, enabling further expansion. The modular design means that further modules could be added as the colony grows, and that could allow more than one astronaut to be supported. Perhaps produce produced on Mars could even be sold on Earth. This could lead to the establishment of an entire economy based off Earth.
That's it?
Yep, that's our
Questions from the judges?
Could you give us an idea of size and material?
Well, really, in terms of size, we haven't really specified that because we're not technical experts. We've come up with a design, and also because it's going to be linked to essentially the living containers of the landing capsule. That would probably be dictated to fairly from whatever design of the astronauts living area.
You must have something in mind, though, because if you're talking about astronauts sunning themselves beneath the vegetables,
Yeah.
You must have something in mind. So what do you have in mind, particularly since this is supposed to be readily deployable and transportable?
So our current, design is based around the idea of the existing module size that you could have. At the moment, it's approximately, we'd be estimating 2 to 3 meters high, and then expanding a further 2 meters, and perhaps about 3 meters in diameter. So it's sufficient room for for 1 or 2 astronauts to be in there at a time, with up to 2 or even 3 columns of trays down.
Okay, so it talks about in some of the functional specifications, I think it goes into, I think it's a neat concept, and I think it's all, the mood music, and it's lovely. However, just going back to some of the specs, have you had any thinking about some of the the water and the required gases and how you're going to transport that, and some of those more. I know you're not a technical team per se, but that's kind of what it's laid out in your objectives here.
Yeah, so a part of that was using the internal space when it's in its undeployed mode. There's a void underneath which gives area for the water and original seeding material and gases to be stored, which would probably be in a flexible bag, or the gases would obviously need to be in a pressurized container. And the idea there is to allow, on deployment, for there to be an external bag as well, so that once it's landed, you can transfer the liquid and the seeding material to the outside of the module.
So what happens, I guess, if some of these astronauts are not really green fingers? Have you thought of any other options if they just for their lives can't grow a crop?
Yeah, well, I guess it's an interesting question. I guess our original idea and design is based around the therapeutic nature of being able to tend the plants directly, and so that's been an emphasis. Potentially there is an opportunity for some automated systems to be included, but we were intentionally kind of avoiding that because the therapeutic nature of actually physically tending the plants was something which we thought would be quite important.
Just one question from me. I just wondered if you had an idea about whether you were looking specifically at, say, the Moon or Mars, or you're more just looking at something that could be deployed across multiple environments?
I think our design ended up allowing the way that we've designed it has made it quite transferable. We did sort of focus on the research we did was around Mars and the conditions there, because it seems like possibly the most feasible place at this point for actually sustaining life. But yeah, we were sort of thinking it would be transferable.
Cool.
All right, thank you very much.